Hello and welcome. In this episode, we're covering the SOHCAHTOA method for right-angled triangles. To begin, let's familiarise ourselves with some key terminology. The Greek letter theta is often used to represent an unknown angle in a triangle. Given an angle theta in a right-angled triangle, it is possible to label the three sides of the triangle with the following terms: hypotenuse, opposite, and adjacent. The hypotenuse is the side across from the right angle. The opposite is the side across from our angle theta. The adjacent is the side which touches theta and isn't the hypotenuse. Let's get some practice applying these definitions. We've got some practice identifying the hypotenuse, opposite, and adjacent. This is a crucial building block when it comes to the trigonometric functions sine, cos, and tan, since each of these is defined as a ratio of these quantities. The sine of theta is defined to be the opposite over the hypotenuse. The cos of theta is the adjacent over the hypotenuse, and the tan of theta is the opposite over the adjacent. A nice way to remember these results is to focus on the first letter of each word. S for sine, O for opposite, and H for hypotenuse gives us SOH. C for cos, A for adjacent, and H for hypotenuse gives us CAH. T for tan, O for opposite, and A for adjacent gives us TOA. Putting these all together gives us the word SOHCAHTOA. If you can remember this word, it will help you recall the definitions for sine, cos, and tan. Some people like to turn the word into a sentence, and there's many ways to do this. My personal favourite is: silly old Harry chased a horse through our attic. Now, let's see some examples of SOHCAHTOA in action. In this triangle, one angle is labelled as a right angle, and another angle is labelled as theta. The three sides are labelled 3, 4, and 5. To find the sine, cos, and tan of theta, the first step is to label each of our three sides. the hypotenuse is the side across from the right angle. Here, that's 5. The opposite is the side across from the angle theta. Here, that's 4. The adjacent will just be whichever side is left over. Here, that's 3. Well, by definition, sine of theta is equal to the opposite over the hypotenuse. Since the opposite is 4 and the hypotenuse is 5, the sine of theta will be equal to 4 over 5. Cos of theta is the adjacent over the hypotenuse. In our triangle, the adjacent is 3 and the hypotenuse is 5, so cosine of theta will be equal to 3 over 5. Tan of theta will be equal to the opposite, 4, over the adjacent, 3. Here's another example. In this triangle, the hypotenuse is equal to 10.1. The opposite is 5.8. And the adjacent is 8.3. Sine of theta is equal to the opposite, 5.8, over the hypotenuse, 10.1. Cos of theta will be the adjacent, 8.3, over the hypotenuse, 10.1. Tan of theta will be the opposite, 5.8, over the adjacent, 8.3. Now that we have a good grasp of our 3 trigonometric ratios, let's see how they can be used to solve for an unknown value in a right angle triangle. In our first example, we are given an angle of 38 degrees, a right angle, and a side length of 12.3. We must find the value of x rounded to 1 decimal place. In the SOHCAHTOA method, there are 3 options available to us: sine, cos, and tan. To figure out which one to use, we should begin by labelling the 3 sides of the triangle. The hypotenuse is the side across from the right angle. The opposite is the side across from the 38-degree angle, and the adjacent is the third side that remains. In our triangle, the opposite corresponds to x, and the adjacent corresponds to 12.3. However, the hypotenuse doesn't correspond to anything. Since we have information on the opposite and adjacent, we should use the ratio which involves these 2 quantities, and that's tan. Another way to think of this is that we have no information or interest in the hypotenuse, so we should make sure that this isn't involved in our ratio. Since sine and cos both involve the hypotenuse, these 2 options are ruled out. So, we've decided that we'll use the statement tan of theta equals the opposite over the adjacent. In our triangle, the angle theta is equal to 38 degrees. the opposite is x, and the adjacent is 12.3. To solve for x in this equation, we need to remove the division of 12.3 from the right-hand side. We can do this by multiplying both sides by 12.3. Performing the calculator work on the left-hand side and rounding to one decimal place gives us the answer that x is equal to 9.6. In our second example, we have a right-angled triangle which contains an angle of 26 degrees. The hypotenuse is labelled x, the opposite is not labelled at all, and the adjacent is labelled as 9.1. Since we have labels for the hypotenuse and adjacent, we should use the ratio that involves these two quantities, cos. Plugging in the values for our triangle tells us that cos of 26 is equal to 9.1 over x. Solving for x is a bit trickier here, and that's because the x appears beneath the line in a fraction. As the first step, we can multiply both sides by x to get rid of this division. From here, all we need to do is remove the multiplication by cos of 26. We do this by dividing both sides by cos of 26. Performing the calculation on the right-hand side and rounding to one decimal place gives us the answer that x equals 10.1. In our final example, we have a right-angled triangle and one of the other angles is labelled as x. The hypotenuse is labelled as 5 and the side opposite x is labelled as 4. The adjacent does not have a label. Since we have labels for the opposite and hypotenuse, we should use the statement which involves these two quantities. Sine of theta equals the opposite over the hypotenuse. In our triangle, theta corresponds to x, the opposite is 4, and the hypotenuse is 5. So the statement becomes sine of x is equal to 4 over 5. To solve for x, we need to remove the sine function in front of the x. We do this by taking sine inverse of both sides of the equation. On the left, the sine inverse cancels with the sine, and we're just left with x. Now we can use our calculator to compute the right-hand side. Rounded to one decimal place, we find that x equals 53.1 degrees. Now that we've seen some examples, it's time to get some practice yourself. To conclude this episode, here are 2 exercises that you can attempt using pen and paper. The answers to these exercises can be found in the video description.